Okay, so we just talked about scatter plots, and we saw that variable r a lot in that lesson. So r actually stands for the correlation coefficient. So double R there, correlation coefficient. Now this gives a direction and quantifies the strength of a linear association between two quantitative variables. And we actually use the following formula to calculate the correlation, r equals 1 over n minus 1. This fancy symbol here is called a sigma, and it means the sum of the observations. And when we see observation minus average over standard deviation, hopefully our mind goes to z-scores when we're using like standardization. So notice that this is just the z-score of x, or the explanatory variable, and this is the z-score of the y variable. And what's important here is notice that it's going to pass through both the average of the explanatory variable and the average of the response variable. So this r formula is really 1 over n minus 1 times the sums of the product of the z-scores for both of our variables here. And we interpret it as the following. There is a direction and strength linear association between the explanatory and the response variable. And of course, we just fill that in with our context, direction being positive or negative, and then a strength of being a weak, moderate, or strong. So what's important here though is that this is specifically for a linear association. So that's why we need the scatter plot to see, is our data actually linear? Because you can calculate r for basically any two quantitative variables, but to see the strength of the linear association, we're going to need that scatter plot. Now, based on this formula here, we have a few characteristics of r that we have to take into consideration. Well, r measures the strength of the linear association between two quantitative variables. So basically, the closer r is to 1, the better the strength is. Now, the sign of r indicates the direction of the association, and that's because if this correlation coefficient is following this trend of the data, and the slope shows us that rate of change between the two variables, they should have the same sign, or the same direction. Now, the slope of the model and r have the same sign as for the previous explanation there. R is always unitless. Since we're using these z-scores here and we're standardizing our values, it's going to be unitless, as it is just giving us this strength and direction of these two quantitative variables. R varies between -1 and +1, meaning that it's either a negative association or a positive association, and then again our three varying degrees of strength. And so that's just going to depend on the sign of r and then what the magnitude of r is, or the absolute value. If r is 0, this would be indicative that there's actually no correlation between the two variables. There's no linear relationship, or any relationship perhaps. They could be independent of one another, or maybe it's a nonlinear relationship. But if you see r is 0, typically that means there's no linear correlation between the two variables. Now, if the absolute value of r is 1, so whether r is 1 or r is -1, this means that there is a perfect correlation between the two variables, meaning that the two variables are changing at the same rate constantly. And we drew an example of this at the end of lesson 2.1 in the last video. And then lastly, correlation does not equal causation, meaning that just because heat rises and ice cream rises and murder rates rise, that does not mean that more ice cream being sold is going to lead to more murders occurring. Correlation does not equal causation. That just means we might see some relationships or association, but that doesn't mean that they cause one another. Now, some things with r, thinking about the U in our Duff's model there, some things that change r is the strength and direction of a linear relationship. So any major departure from this linear pattern is going to change r, meaning that if you see a point that's really far away, that's going to change the degree of r there, that magnitude of r. Some other things that could change r include over-predicting, meaning that if I gave you data between 2015 and 2020, and then you tried to predict data way in like 2035, 2040, that's going to change r because that is a way off explanation, and I don't know if the data for those 5 years holds true outside of that range of values there. Now, because r is the product, right, the sum of the products of the z-scores, we know that if I swap the variables, if I swap zx and zy, that's going to be okay because it's still the sum of those two products. Or if I change the units, again, I'm converting one of the z-scores, it's okay because it's a standardization. So swapping the variables or changing the units is not going to switch up r. Again, what does switch up r is those departures from the linear pattern. Now here we just have a few examples. This lesson's actually pretty short. You're going to be combining the correlation coefficient and the scatter plot, so it's like very rare to see them independent of one another. But nonetheless, here we are. So let's go ahead and match the correlation coefficients to their correct graphs and write the letter in the space. So A, B, C, D, E, F. And you can see here we have some negative ones, we have positives, and then we have a 0. So what I'm doing here is I'm essentially looking at the slopes, and that will help me determine my direction. And then I'm looking at the degree of clustering, and that will help me determine my strength. So let's do the obvious easy one. 0 is one that just looks like there's no relationship. So I look here, this one's got a positive one, this one's relatively negative, oh, very positive, negative, kind of positive, but this one right here at F absolutely got no business doing nothing. So we'll put F right here at the 0. Okay, so that takes care of F. Let's look here at 0.99. That is so close to 1. That's going to be almost close to perfect correlation. That's going to look like scatter plot C here. Okay, so then I can look at my 2 negatives and my 2 positives. And 0.33 is weak, whereas 0.87 would be considered strong. So my 0.33, I need a weak and positive. Well, my only 2 positive options are A or E. So 0.33 looks like it'll go to option E. 0.87, strong and positive, that's going to go to option A there. And here you have negative 0.85, negative 0.4. I think you can do those last 2 on your own. And then after you do matching those 2, go ahead and rank here the correlations from weakest to strongest. Notice that it's not taking into account the direction, it's just taking into account the strength. So go ahead and pause the video here, try out the remaining examples, and we'll come back and review those together. So reference your notes from 2.1 if needed, or the section above here. So go ahead and pause the video and take some time here to answer the questions. All right, so hopefully not too much more complicated. You should have gotten that B. You notice that it's relatively weak and negative, so that would be assigned to that negative 0.4 correlation. And then D, it's negative, but the degree of clustering is significantly closer together than in scatterplot B. So that one's got a stronger predictive power. It should have a higher correlation coefficient. So D would be matched to this negative 0.85. Next up in that following example, it says rank the following correlations from weakest to strongest, meaning I'm going from 0 to 1. And sorry, here, let me add my notation here. I looked at the absolute value of R. Because again, the strength is measured by the absolute value of R, the direction is just given by the sign. So my weakest one here would be positive 0.08, because that's closest to 0. The next weakest one would be negative 0.4, because that's still weak, and the negative sign doesn't matter, because the absolute value is still 0.4. Next up, we'd have 0.43, we're getting closer to 1. From there, we'd go up to 0.8. Sorry, not 0.8, 0.79, positive, 0.8, still positive, getting closer to 1. And then our closest one that has an absolute value closest to 1 is going to be there at negative 0.82, which is correlation number 4. So that's just an idea there. This correlation coefficient measures the strength and direction of the association, of the linear association between 2 quantitative variables. And then again, this helps us to describe the trend of the data as well as the strength of that model there. So now we know a little bit more about scatter plots and the correlation coefficient. So next up, we're going to talk about actually using this model to make predictions. So stay tuned.